Hello everyone, welcome to today's switchboard training. My name is George Roscoe. I'm the product manager for switchboards and power panels. Today's topic is Switchboard Basics. It'll be the first of several topics on switchboards. I recommend taking this class first because this one is going to start from the very beginning. Today's training is going to focus on a high-level overview of what is a switchboard and some of the key components of switchboards. Then we'll talk about the different types of distribution switchboards that exist and what goes in them. And then at the end we'll talk a little bit about what replacement parts are available. Let's start first by talking about the overview of switchboards. What a switchboard is and what goes into it. The image on this page actually shows a good representation of several different types of switchboards that we have. The right two are illustrations of distribution sections. The middle one is a skinny main, which is an example of our standard incoming section for mains. And on the left is an IPS, which we will talk about in a different trim. According to the National Electric Code, switchboards are defined as a large single-panel frame or assembly of several panels on which, mounted on the face, back, or both, switches, overcurrent, and other protected devices, buses, and instruments are mounted. Essentially, switchboards are a large set of panels interconnected via busing. They carry current from one side of the switchboard to the other. It normally sits at the top of a commercial distribution system for low voltage. It is made in several plants across Siemens. It's made in Grand Prairie, Texas as the primary plant. Pomona, California, and Spartanburg, South Carolina handle our less complex switchboards on a regional basis. And recently, Drummondville, Quebec has come on as our plant for stock switchboards. There are two major standards that switchboards follow. Namely, the main standard bearer for the United States is UL 891. That is the standard for switchboards that us and all competitors comply with. Secondly, there's an offshoot of it, NEMA PV2, which is the NEMA definition of a switchboard. Typically, and in most cases, our switchboard designs are built to comply with the National Electric Code. For example, things such as ground fault on 40-volt systems, we ensure that we have a solution that will meet that. The maintenance mode required by NEC 240.87 is something we offer in switchboards as well. Sometimes the offers are options, sometimes the features are standard. It depends on your region and if it's required by National Electric Code across the country, or if it's specific to a given version of the National Electric Code. A switchboard is at the heart of an electrical distribution system on the low voltage side. Here's an example of how a switchboard fits an electrical system. In cases where the customer may have medium voltage equipment on site, such as medium voltage switchgear, you can see that switchgear would feed a transformer that would step the medium voltage down to a low voltage, typically in the US either 480 or 208. And at that point, the power would come into the switchboard. And then the switchboard acts like a distribution system to all the lower loads, such as feeding transformers that would feed lighting panels, or to motors that may be used at 480. Switchboards can also feed other things such as directly to lighting panels and power panels. The way to look at a switchboard is, in a commercial and light industrial application, it is the heart of the low voltage system. One of the most common questions asked is, when is switchgear used versus switchboards? They're very similar and they're different at the same time. Here is Siemens' two offerings. For switchgear, we sell type WL switchgear, and for switchboards, we sell SV switchboards. One way they're different is the standards they follow. Switchgear follows UL 1558, also known as IEEE C3720.1, while switchboards follow UL 891. One thing that is similar is they both can have through bus running through them that is 5,000 amps, and in both cases there's also 6,000 amp through bus. So the ampacity that they can cover occupies the same range. The same can be said about voltage. The voltage is set to similar levels whether it's switchboards or switchgear. The only difference is the switchgear standard has the voltage go up about 10% higher than it does in switchboards. One big difference is switchboards are designed from a commercial aspect where value engineering can be important. So switchboards come with both copper and aluminum busing, whereas switchgear is copper busing only. Another big difference is switchgear typically only uses draw-out power circuit breakers. In the Siemens world, that's WL breakers. In the switchboard world, we use draw-out WL breakers, we use the fixed version that do not have a cradle, We use multi-case circuit breakers and fuse switches. There are many more cost-effective options in switchboards, and often that is because there's smaller breakers in switchboards. They can have the same size breakers, but they're more likely to have more 250 amps in switchboards than you have 250 amp WL breakers in switchgear. The other big difference is the access. Most switchgear requires front and rear access, as the cable terminals are in the back of switchgear. Switchboards are designed to be front accessible, as long as they are under 40 inches deep. What that means is all cable terminations are able to be made from the front, as well as all electrical connections. There is no need for rear access during installation, typically, or during use. Finally, one of the biggest differences between switchgear and switchboards is the withstand test of the busing. Switchboards are designed to only handle a short circuit event up until the breaker opens. Switchgear is designed to handle a short circuit event for basically 60 cycles without any interruption. This means the bus has to be much more hardened than switchboards, as it is designed for uptime, which allows the breaker closest to fault to clear, hence why it has that longer withstand time. The heart of the switchboard is defined by its envelope, or the frame. Our standard height is 90 inches. All of the standard designs are at the 90-inch level. There is an optional 70-inch with limited standards and mostly custom options available for when you cannot fit a full-height switchboard. The width and depth of switchboards are very dependent on the devices in it. For example, a group-mounted distribution section needs to be at least 32 inches wide. A skinny main section with a WL breaker would be 25 inches wide. A draw-out 5,000 amps WL circuit breaker needs to be 46 inches wide. So the width is dependent on the devices and the features required. The depth is a product mostly of ampacity. At 28 inches, you can be up to 2,000 amps, 38 inches up to 5,000 amps. 48 and 58 inches are custom designs based upon needs for additional wire space or additional hardware need to be placed in the rear of the gear. Other special sizes are available depending on customer requirements. We prefer to stay within our standard frames, but if need be, there are some options for some intermediate frame sizes and levels. Busing is one of the key pieces for distributing electricity throughout the switchboard. There are two types of bus. Horizontal through bus, which is used in almost every section of switchboards, connects the main incoming power to all the other sections of the switchboard. It's available as through bus from 400 amps all the way up to 6,000 amps, in both aluminum up to 4,000 amps and copper all the way up to 6,000 amps. The bus can be tapered or non-tapered. Non-tapered means the horizontal through bus is fully rated throughout the switchboard, and tapered means that as you get further from the source, the ampacity of the through bus goes down just to serve the loads it needs. Vertical section bus is used in distribution sections. It's available from 400 amps to 3,000 amps. There's new designs available that allow you to have a center fed design where you can have basically two 3,000 amp distribution sections in one area, which effectively gives you 6,000 amps of busing. The most common busing material is 65C aluminum. There's also other options such as temperature-rated copper, 65C copper. We also have custom designs of amp per square inch copper and aluminum. Aluminum is standard as tin plating, and copper as standard is silver plating. We can do tin plating on copper. It adds some lead time and some cost, but it can be done. The default choices in our configuration tool are temperature-rated aluminum, and the second choice is temperature-rated copper. Slightly more switchboards are aluminum than copper. The image on the left shows the phasing of the switchboard, with A phase being at the top and the neutral being at the bottom. The way we make connections between sections is through a splice plate. As you see, the splice plate is shown in the image on the right as having a Belleville washer on it, and then an extension that would slide into the next section to be bolted down in the following section to make an electrical connection between section 1 and section 2. In this view, showing something very similar to the previous page, shows the splice plates and then the Belleville washer on the next section, where you'd slide the splice plate into place and then bolt down the connection to make the two sections become effectively one flowing power supply. Here's an example of a typical distribution switchboard. The incoming is in the section on the right with the utility metering section on top. The key giveaway there is that the busing is mounted through, spaced out, and would allow for CTs and PTs to be placed on it. The other giveaway that's the main section is that they have an individually mounted main breaker. That is very common, and most of our breakers are individually mounted mains. The second section is a distribution section where you have several breakers mounted horizontally in unit space going from the through bus to the front of the gear, and have load lugs that can be taken out to feed devices outside the switchboard. This is a very common configuration and used in several thousand sections a year quantities. Taking the visual on the other page and representing it as a one-line type diagram, we have an incoming supply coming in, then we have a circuit breaker that is the main, connected through horizontal bus to feed the group-mounted branches that feed loads outside the switchboard. This representation is an electrical version of the visual we saw on the previous page. Here's a front view of an actual switchboard with the covers removed. The first section on the left is the service entrance section. It is very important in switchboards that you define whether or not it is service entrance or not. The way you do that is by saying, is this the first disconnect switch from the utility? If it is, it's service entrance. If the customer owns gear upstream that can be turned off, then it can be considered non-service entrance. When you get a service entrance board, there'll be some additional varying on the line side of the main breaker. The second section is our group-mounted distribution section. It shows all the different multi-case circuit breakers mounted horizontally in space. If you look at the bottom, you can see where the neutral connections are made at the very bottom of the switchboard. Looking to the far back, you can also see the through bus, which is connected between the main and the distribution section. Going back to the left, on top you can see a meter. This is considered a customer metering compartment. What that means is this meter is there for the customer's information, not the utility. One of the key ways to tell that is if it is a Siemens meter, a Shark meter, or some other type of meter that is not utility grade or utility branded. The next thing you see is in the section is lugs, incoming lugs. That means that you have cable incoming that terminates right into the gear at that point. And right below the lugs, power is fed to the main circuit breaker. That is the main disconnect for this board. Also, at the top and bottom, there will be vent holes for cool air circulation. These vent holes allow us to meet our UL temperature rise requirements while maintaining a cooler environment than if there was no venting. Item 7 is now in the distribution section. You can see a space to install additional breakers. One of the most common questions I get asked is, do I have enough room to install another breaker? Well, this is one of the important things when we look at Compass you'll need to consider is, do I leave space in there? For example, for more 250 amp or 400 amp breakers. In this example here, you see plenty of room for 250 amp breakers, as their breaker right above that space is actually 250 amp breakers. Item 8, which we talked about briefly before, is the through bus. You can see that in this case the through bus extends all the way through the distribution section, indicating it's non-tapered bus and that it can be used to add another section in the future. 9 is the side space next to the breakers where you can run your cables when you're doing your distribution section. They can either run through the top or bottom of the gear, and they would then feed the loads downstream. And then back on the left, item 10 and 11 are, item 10 is a meter, which is the customer meter, and item number 11 is a test panel to test the ground fault scheme of the system. Here is the same switchboard seen in the previous slide from the rear. Now on the right is the main section, and on the left is the distribution section. You can see the service entrance section and the distribution section have been flipped. Item number 3 is the customer metering compartment, so you can actually see the auxiliary compartment mounting in the rear. And then item 4, which is the top 3 through buses, are the phase A, B, C through bus. And then item 5 is the neutral bus, which is at the bottom. You can also see the ground bus is running towards the front of the gear, item 6. And then if you look, also you can see in the distribution section the 3 phase buses there. You can also see where the side wiring goes and the bolted splice plates, which are in the middle between the 2 sections. Now we're going to get into the different types of distribution switchboards, which are broken into 3 specific categories. There are 3 types of switchboards available in the SB class. SB1 is our most basic switchboard typically at about a 5-week lead time. This involves 2000 amp through bus and below, 65 kA interrupting rating and below, temperature rated copper and aluminum only, thermomagnetic molded case circuit breakers, basic meters, and fuse switches. SB2 switchboards have all the features of SB1, add electronic trip circuit breakers including our WL power circuit breakers, go up to 4000 amp through bus and 100 kA. SB3 is everything else. It's 5000 amp through bus, 6000 amp main bus, 5000 amp main breakers, rear accessibility, custom designs, and any special manual modifications to be made. These three classes drive lead time. So SB2 is 7 weeks typically, SB3 is between 10 and 12 weeks. One thing I want to make sure people are aware of is an SB3 board can be cheaper than an SB1 depending on the technical differences, such as it could be a simple add of a special type of door versus the Conta SB1 could have more breakers. But there are some things that need to be considered. On large projects, the discount schedules for SB1, 2, and 3 approvals will be different. Now we're going to go through the common incoming selections and main device and branch device selections of switchboards to get you more familiar with what is available in switchboards. The next few slides will talk about the available incoming connections. By far the most common incoming connection is cable. Cable connections can come into two different types of lugs. The one illustrated on the left here is a mechanical lug. Mechanical lugs are typically the most common. They'll either be directly connected to the breaker or connect off of the breaker. Mechanical lugs are designed for standard either copper or aluminum wire, and they vary in the size and number of cable connections that they take. So one important thing when you're doing incoming estimates is make sure you specify the number of conductors and the size of the conductors to ensure that you get the right amount for your switchboard. Busway is the second most common incoming solution. In fact, there are standards for busway incoming for Centron busway into an SB switchboard. Basically, as you look in this image of the WL breaker, is our flanged end of the busway comes into a connection at the top of the gear. If you look at the flanged end of the busway in the bottom right of the picture, you can see how it would fit through the hole in the top of the switchboard and then connect right into the through bus there. We can also do other competitors' busway entrance, but measurements and dimensions are critical in this manner. That's why we prefer using our Centron busway where we have standard designs already available. The third type of configuration is a transformer connection. Transformer connections are typically done on unit substations, where we have a fused medium voltage switch feeding a transformer that then feeds either switchboard or switchgear. In this case, what we do is we take in the transformer connection these vibration absorbing flex cables that connect between the transformer and our bus. The flex cables absorb vibration, therefore preventing screws from coming loose on the switchboard side. These are only typically used for transformer connections to unit substations, so these are fairly rare. Probably about less than 2% of the volume is a transformer connection. But it is very critical when designing these that you specify the transformer, just like the busway, to ensure we put the connections in the correct spot. Bus splice is the rarest of all the incomings. This is when you're adding to existing Siemens gear, and it only can be done on existing Siemens gear that has non-tapered bus. If it has tapered bus, you will not be able to make this connection. So if you think that you need to add on in the future, make sure you add future end section so you can add this feature and select non-tapered bus. Typically, in our compass configuration tools, wherever the incoming is, we try to terminate it in the same section with the disconnect in that section. There are two types of pull sections that allow a little bit extra space for install. The first is non-bus pull section, where the cables come in a section next to the main and then are routed into the main section where they're terminated. The second is a bus pull section, where they are pulled in a section of the cables and then terminated in that section, which then bus brings over to the next section. Compass will determine when a pull section is required by space restrictions or other needs, but you can also manually select it if needed. Main device options are very varied in switchboards and have the most options of any electrical equipment in low voltage. The first is WL circuit breakers, which are considered power or insulated case circuit breakers. We have options for main devices that can either be UL489, which is standard, or UL 1066, which is the switchgear breaker. The two options we have for WLs, besides being mains, is they can be mains from 800 to 5,000 amps. They can either be fixed mount or draw out. And what that means is fixed means the breaker is mounted with nuts and bolts and can't be removed without hardware. Draw out means there's a specific design cradle that allows it to be racked in and out. The second most common type of main after WLs is multi-case circuit breakers. At Siemens we have two families we can use. Centron, which is our thermomagnetic option of choice, which goes from breakers as small as 15 amps all the way up to 2,000 amps thermomagnetic. We also have solid state in the 400 amp frame all the way to the 1600 amp frame. The VL breaker is our choice for solid state mains and solid state breakers in general. From a main standpoint, it can be 400 amps to 1600 amps electronic trip. For feeders, it can go from 30 amps to 1600 amps. And for thermomagnetic, they go from the 800 amp frame to the 1600 amp frame. Multi-case breaker mains can be horizontally mounted in group distribution up to 1200 amps. And anything larger will either be individually or combo section mounted. We'll show some examples of that on the next slide. Then finally, we also have fuse devices that can be mains. And these fuse devices are typically one of the three types. Vacuum brake switches are a preferred method if they are 600 amps or smaller for mains. High contact pressure switches up to 1200 amp mains. And bolted pressure switches anything larger than 1200 amps all the way up to 6,000 amps. And just as another note, bolted pressure switches above 4,000 amps will not have a UL label. There are several different branch options available on switchboards. This slide will take you through some of the most common. One of the most common main options is WL breakers, but they can also be used as larger size feeders. WL breakers can be individually mounted from 800 amps all the way up to 5,000 amps as feeders. We have combo and 2 high sections available up to 2,000 amps, which we'll get into some more detail in a future training session. You can also use the 2 high as shown here, which is not gyro pull section. There's also several custom side-by-side options available for the WL. So it's a very flexible, low density mounting option as a feeder. The next is a bolted pressure switch, which is a fused switch with a disconnecting means. It can be mounted individually up to 5,000 amps. As a side note, any bolted pressure switch over 4,000 amps will not have a UL label. It'll only have UL label on 4,000 amps and under. You can combo bolted pressure switches with group mounted distribution up to 2,000 amps. You can mount up to 2 1200 amp bolted pressure switches in a site. Individual sections, as mentioned, can be used from 800 amps all the way up to 5,000 amps of bolted pressure switches. Multi-case circuit breakers. This can either be group mounted or they can be individually mounted. Above 1600 amps, they'll have to be mounted either individually or 2 high mounted or combo mounted as shown here. This is a 2 high example of 2 Centron breakers dual mounted. We also have custom side-by-side available as well. Vacuum brake switches, they can be mounted in group mounting up to 600 amps. And anything larger, you can do branch mounting 2 high up to 1200 amps. And then we have twin mounting, as you can see in the 6th section of 2 of them. There is no combo section available with vacuum brake switches. High contact pressure switches are our best choice when you need to group mount fuse switches above 600 amps. They can be panel mounted up to 1200 amps, and they are allowed in vertical and horizontal mounting. Combo and 2 high vertical sections are not available, and if you need to use that feature, use the vacuum brake switch. Multi-case circuit breakers are typically horizontally group mounted up to 1200 amps. We can dual mount up to 400 amps, which is a Siemens advantage because we can mount 400 amps in under 30 inches of unit space. Another key advantage for us is the installation options. We can install them. We can put provisions which give you the straps to install a breaker at a later date or a space. These options are available when group mounting circuit breakers, and typically we'll see provisions used if the customer knows that they're going to need a specific type of breaker in the future, and we'll see space used if they're unsure but want to make sure they have adequate space to add something in the future. Outside of devices, one of the most common other features of switchboards is customer metering compartments and utility metering compartments. These compartments can be placed in one of 3 areas. They can be placed on an incoming section like a pull section. They can be placed above an individually mounted device such as a breaker, as you see in the middle picture, or they can be mounted in distribution with next to a branch device. The big caveat here is when it's in its own individual section or an incoming, there is lots of space, typically can fit multiple meters, multiple SPDs, and a lot of other auxiliary components. If it's panel mounted, you're very limited in space and only can typically feed 1 meter or one specific feature. Utility compartments will depend on the local utility. Some of them, called hot sequence, are measured before the main disconnect, and some of them, called cold sequence, are measured after the main disconnect. Some examples of things the customer will have is analog meters, digital meters such as pack meters, surge protected devices, relays, contactors, pilot light devices, transducers, special equipment for communication, and many other things. As mentioned earlier, options can be mixed in compartments, specifically the full-size compartments in incoming and individually mounted sections. And for example, you can fit up to 10 meters in a 30-inch individually mounted auxiliary compartment. In conclusion today, we went over the basic parts about switchboards, the different incomings from cable to busway, the different main devices, whether they're circuit breakers or fuses, all the different branch device configurations, and then we concluded with the different types of compartments for auxiliary usage for the customer, as well as for utilities briefly. Hope you enjoyed today's session, and thank you for your time, and we look forward to you attending another switchboard training session soon.